Morning. This is day 2 of the quarantine distance learning, and I am going to look at some of the slides we were looking at the other day with solubility. My goal today is to kind of finish the slides. This will finish chapter 16 for us in the AP chemistry. I definitely intend by tomorrow to be looking at chapter 17. Solubility, we did a lot on Thursday, pretty easy topic. There's some nitty gritty stuff that we'll look at today. If you were to read along in the textbook, there's a lot of like excess material that I don't think we have to worry about. No one really knows what the AP exams will look like, but I am still operating under the assumption that May 7th, we will be taking some type of exam, and if we have to adjust, that is fine. But I think that it's important that we do as much as we can because this whole situation is trying enough on its own. So we might as well try to keep something normal so we have this goal in mind. So when we left class on Thursday, last time we saw each other, so sad, we were talking about Q and the solubility product. So they're set up the same way, all right? So in these solubility reactions, we don't include the reactants because they're always a solid. So Q is equal to the concentration of the products raised to whatever powers based on their stoichiometric coefficients. KSP, it's the same way. And we were looking at what happens to form an actual precipitate. So Q has to be greater than the KSP to get a precipitate to form. All right, we can have a compound that we have listed as insoluble, but if we have it in small enough concentrations, those reactants won't find each other. All right, they won't reform the solid. So if we have really small concentrations, again, that's really small Q, a precipitate will not form even for something like a lead iodide, right? Lead 2 iodide that we know should form a solid, but it only will if Q is greater than KSP. So for those really soluble compounds, they have really tiny KSPs. But even something like sodium chloride, that's going to have really large KSP. It's going to favor being dissolved. We know that when we pour salt into water, it will dissolve. But if we pour too much salt, it will become supersaturated, and that will be the precipitate, right? That's Q greater than the KSP. So even though something like salt might have a really big KSP, if the Q is larger, we will get the solid. All right, so we were looking at this question. I believe we worked through it. The 25 mLs of the 0.002 molar potassium chromate mixed with the 75 milliliters of the 0.000125 molar lead 2 nitrate. We are given the KSP. It's important that since we are mixing solutions, we're diluting. Here we have the 25 mLs and the 75 mLs. We need to add the volumes, right? We're going to assume that these volumes are always additive. The nice questions, and you'll see some of these in today's daily assignment, the nice questions give you the same volume of each, so you can just cut the molarity in half, all right? Those are the nice ones. Here we would have to work it through. We need the reaction. The interesting thing, these types of questions, when we're trying to figure out if something's going to precipitate, both initial reactants are soluble. So it's potassium chromate, lead 2 nitrate. So you got to figure out which one do you think may form the solid, and it's the lead 2 chromate. The KSP is not always given. So if it's not, you would want to be looking that up in a chart. So we have our reaction, the Pb2 plus the chromate forming the PbCrO4 solid. All right, and from the reaction, because we need to balance it, and this one's easy, it's a 1 to 1 to 1, we get what the KSP should look like, right? Pb2 plus times the KrO4 minus. So now we're able to come up with the new molarities of each initial solution. So the potassium chromate has been diluted. Now it's 0.00050 molar. And that 0.00050 molar is the concentration of the chromate ion, all right, because of the way it will split apart. All right, we would do the same thing for the lead nitrate, and the concentration of the lead nitrate is the concentration of the lead 2+ ion. For the nitrates and the potassium, they would actually be doubled, right? We see those subscripts, so we know that when they dissociate in water, you would make twice as much of that particular ion. So you would multiply the molarities by 2. That is not what is happening in this question. So just something to be cautious of. All right, this question was pretty nice to us. It gave us things that are in 1-to-1 ratios, but just always something to be aware of when we're working through these questions. All right, so now you're able to calculate the Q, right? You put in both the concentrations. We don't have any exponents here because the coefficients from the reaction were 1, so that's nice and easy. We get the 4.69 times 10 to the negative 8th. All right, that is greater than the KSP. Precipitate will form, right? Q is greater than KSP, precipitate will form. If Q is less, the precipitate will not form. All right, we have this practice question. I didn't work it through, but something to be aware of. We do get the nice numbers, 100 mLs of the magnesium nitrate, 100 mLs of the sodium hydroxide. So when we go to do the magnesium hydroxide, since we add up to the 200 mLs as the new volume, this means we're gonna have a 2.0 times 10 to the negative 4th molar magnesium 2+ solution. And for the sodium hydroxide, we're going to have 1.0 times 10 to the negative 4th. You would be plugging those numbers into the KSP. That would be the concentration magnesium times the concentration of hydroxide. So it's going to be 2 times that squared. All right, and you're going to compare it to the 8.9 times 10 to the negative 12. So you can do that practice on your own. All right, so what I wanted to talk about today, I think this is kind of cool. It's one of our last topics for chapter 16. This is something called selective precipitation. So it's a flow chart, and we go in the same order. Add HCl, add H2S, add NaOH, add Na2CO3. So this would be like a common practice that a chemist would use. You would be given an unknown compound. It's going to have one of these ions. You are trying to figure out what it is. You're going to add these 4 solutions, and you're going to see if a precipitate forms or not. All right, so this is a way to identify an unknown compound. So that's why it's being used. Another way to identify cations, and it's not perfect, but we can also use the flame test, right? That's where you burn it and you see the color it produces, but some of those colors are really blurred. They're very similar to each other. So that may be something we would do towards the end of the test. All right, but at the beginning, you would add hydrochloric acid. All right, the point of that is to provide Cl- ions, which will form an insoluble chloride with either silver, mercury 2, or lead. So if you add hydrochloric acid to your unknown and a precipitate formed, you know it is one of those 3, either silver, mercury, or lead. All right, and then you can do further tests to try to identify which one it is. All right, but on your first pass, if no precipitate forms, you know you don't have silver, mercury, or lead. All right, now you add the hydrosulfuric acid, the H2S. That sulfide ion, the S2-, all right, a lot of things are insoluble with it. So if you get a precipitate, you know it's either going to be copper, bismuth, cadmium, lead, mercury, arsenic, antimony, right? It's going to be one of those. So it's a new pass that we're going to go to get an idea if something is, if it's one of these cations in our unknown. All right. Now, let's say you've added hydrochloric acid, you've added the hydrosulfuric acid, still no precipitate, right? All of these cations are off the table. So we're still trying to figure out what the unknown is. Now we add the sodium hydroxide. All right. Hydroxide salts are very insoluble. So if we have made it this far, this is going to let us know if we have aluminum, if we have iron, if we have nickel, zinc, chromium, cobalt, manganese. For the hydroxides, we get a lot of those first row transition metals, right? So whereas with the hydrosulfuric acid, we get a lot of those transition metals that are underneath the metalloids. Now, with the addition of sodium hydroxide, we are testing for a lot of our more common transition metals. All right. Now, again, if we still have no precipitate at this point, right, we have crossed all of these off. This is like the chemist's version of Guess Who. All right, that'd be a great game to make. You know, the chemist guess who, and you can add different solutions, and you would have to cross out the different insoluble ones. I think that'd be an excellent game. So, you know, maybe that might be in development over this quarantine. The last test we add is we add sodium carbonate. All right, carbonates are more soluble than everything else we've seen, but we have three big exceptions: barium, calcium, and magnesium. So if we've made it to the end of our selective precipitation flowchart, adding the sodium carbonate will test for our group 2 metals. All right. Now, we will never in the selective precipitation find a group 1 metal or ammonium, because those are always soluble. All right. We would have to add them in such large amounts that they would precipitate out because of Q, but that's not part of this test. All right. So it's a way to identify an unknown. It's a way to attempt to identify an unknown. And then once we get an answer from one of these 4 tests, we can use other tests. All right, we can look at the molar mass, all right, by doing a gravimetric analysis. We were doing that back in the fall. We could do a mass spec. There's a whole bunch of tests we can do to further narrow it down, but this is a very simple one that any chemist can do quickly in a lab, just adding a little bit of each solution in order and seeing when a precipitate forms, if any at all. All right, now something else I want to point out with selective precipitation. All right, we have an example here. It is a solution with chloride ions and iodine ions. All right, and it's going to be titrated with silver nitrate, which, again, I just can't state, like, I cannot believe we're not going to do another titration. It's completely over, and we could have done this, and it would have been a lot of fun. But you'll never get to do that again for these next couple of weeks because we got to move on. All right, so when we add the silver nitrate, silver wants to form a solid with both the chloride and the iodide ions. All right, the chloride precipitate will be white in color, the iodine one will be more yellow. So what's going to happen is when we add silver nitrate, especially if we add it slowly, all right, we're going to get one of them to precipitate first. So what's going to happen is all the iodine precipitates before the chlorine. So we see the yellow precipitate first, then we start seeing the white precipitate. So why does that happen? Well, provided on the bottom here, we have the reactions, right? We have the equilibriums, and the KSPs are what we're going to really hone in on. Silver 1 iodide has a KSP of 8.5 times 10 to the negative 17th. Silver 1 chloride has a KSP of 1.8 times 10 to the negative 10th. Now, we know that Q has to be greater than KSP to get the precipitate to form. So since the silver 1 iodide has a much lower KSP, it's going to take less of the silver nitrate to get it to precipitate. So essentially, since this number is smaller, when we start adding the silver nitrate, the Q will be greater than this KSP first, which is why if we add slowly, we'll see the silver 1 iodide form first. We'll see that yellow solid first, then we will see the white. All right, so selective precipitation also is something we should be thinking about when we look at the KSP values. All right, if you were to do this in lab, I'm sure there'd be one group that would just add it way too quickly, all at once, see both form at the exact same time, inconclusive data. All right, but just be cautious. This is actually, I think, a really excellent AP type question. If they give you 2, which will form first? And all you're doing is looking at the KSP. As long as you know this single fact, you can answer that question, you can move on. All right, now complex ion equilibrium. This is in the textbook. A complex ion, these are kind of cool. I didn't really learn about them till I was in college, so I was taking analytical chemistry. So for everyone that's sitting here and thinking, I just want to know exactly enough chemistry to pass this AP exam and move on with my life, this is the stuff that you're like, well, I want to pass the AP exam so that I can take more chemistry classes in college, obviously. All right, but a complex ion, it's a central metal cation bonded to one or more molecules or ions. So it's always a metal, and the metal goes in the middle, and there's a reason why it's going to be a metal, and it's going to have these other molecules that attach to it. Those other molecules, they are called ligands. All right, you will not see the word ligand on the AP exam, so you should not have to worry about that. You may hear it in a college class, though, if you go on with chemistry. A ligand is basically a Lewis acid base, Lewis acid, I believe. It has a lone pair, right? So the lone pairs from these outer molecules, they are attracted to the open orbitals in the metal, right? So typically, a lot of these are transition metals, what we see in our complex ions, right? And they have space for electrons that aren't being used. So the lone pairs of these other molecules get attracted to it. And it's typically the same couple of Lewis bases, right? NH3, H2O, Cl minus, right? So they come together. So in this example, we have cobalt, 2 minus, and when we have the chlorides, it kind of comes together, right? So this is COCl4 with the 2 minus. This is a complex ion, and it's blue in color. And we saw this actually when we did that Le Chatelier lab in the past, right? Where we were able to add the chlor and get kind of go back and forth between the pink and the blue. But so in the reaction, right, we have the metal plus the ligand, what's going to surround it, and now we have it together. The charges kind of stay together. So the cobalt is 2 plus, the chloride is 1 minus, but there's 4 of them. So the COCl4 has a 2 minus, and we have a formation, right? So the K of formation, the formation constant. And so again, it's products over reactants, and the Cl is being raised to the 4th power. And we're being told that the higher the Kf value, the more stable the complex. So that should seem pretty logical, right? The higher the K value, the more the reaction is shifted to the right, and it favors being in this state. So what does it look like? The metal is an ion, right? And the ligands, the Lewis bases that are attracted to it. So Fe3 plus, iron has those spots, right? Those open orbitals in its highest energy level, right? We know that the transition metals can be a little funky where they can kind of move their electrons out. That's why they get different positive charges, right? They can lose different numbers of electrons. And so all of these water molecules, and here there's 6, right? Fe, H2O, 6, and often we do use the brackets and then put the charge on the outside. So this is kind of what it looks like, all right? The lone pairs are attracted to the metal. Now the molecules still push each other out of the way. It's gonna use the exact same shapes that we got from the Vesper diagrams. So here, when we have 6 groups around the iron, it's an octahedral shape, right? All 90-degree angles. So those beautiful structures, those molecular geometries that we've learned, they still apply to these complex ions. Now, there are 6 ligands attached to the iron, right? 6 of the water molecules. And again, I'm referring to the water molecule as a ligand. It's a Lewis base. It's attracted to the open orbitals in the iron cation. So that 6 is going to serve as our coordination number. The coordination number is how many ligands are around the metal, all right? The coordination numbers are typically 2, 4, or 6. They're typically even numbers, 2, 4, or 6. 6 groups is the octahedral. 4 groups, you may remember, is the tetrahedral, and 2 groups is a linear shape. All right, so here's what 2 groups look like. This would be Ag with 2 NH3 ligands around it. It's a linear shape, right? The NH3s want to be as far away from each other as possible, but it is the lone pairs in the nitrogen that are attracted to the silver. All right, CuCl4, tetrahedral shape, and the COH2O6 has that octahedral shape, right? Coordination number of 2, which just means there's 2 of these groups. Coordination number of 4, coordination number of 6. So nothing much to it. So here's an example of mercury iodide. So mercury iodide as a solid, yes, it could form Hg2 plus 2I minus, but it's Ksp 4.0 times 10 to the negative 29th, right? So it's only going to make a very small amount of these ions. It's typically going to favor being a solid, right? That's mercury 2 iodide. But look at mercury 2 plus. When we have 4 iodines, it likes to form this complex, HgI4 with a 2 minus. All right, so the Hg is the central cation. The iodine is acting as our ligand. It's got the lone pairs, so it's attracted to mercury because mercury has those open orbitals. It's got a coordination number of 4, and the Kf, the formation, it's 6.3 times 10 to the negative 30th. Right? So this top equilibrium favors the reactant side. The bottom equilibrium favors the product side. So the net, if we were to put both reactions together, all right, we would cross out some of the iodines. We would get AgI2 solid plus 2 iodine forms AgI4 2 minus. So what is the K equal to? Well, the K, when we're looking at a solid that can form a complex ion, it's the KSP times the KF. So we would multiply these two numbers together, and we now get 2.5 times 10 to the second. Now that is a number larger than 1, so it's going to tell us that the reaction will move to the right. It will favor the products. So the large value indicates that the reaction proceeds to the right. We will form this complex ion. So we may see some questions like this. We would be given both. You would not be expected to just pull that complex out of nowhere. You would be given it in a prompt, but we can multiply both K's together and that will give us an idea. If it's a number larger than 1, then we're gonna form the product. And again, think about just our equilibrium. If we get a K that's still less than 1, right, 10 to the negative something, then it's gonna probably favor being the insoluble solid. All right, lots of different complex ions exist. We have measured KFs for them. We have the equilibrium reactions. The equilibrium reactions can be written in steps. So something like Fe3 plus 6 Cn, it would be Fe plus 1 Cn forming FeCN, FeCN plus 1 Cn forming FeCN2, FeCN2 plus 1 Cn forming FeCN3. We could do it in steps. You'll see that in the textbook. You'll see it in one of today's daily problems. So it's not that complicated. So just remember, keep track of your charges, just add them up. So something that I want to look at today, I'm going to leave us with this. I will try to make another video later today, kind of going over the answers to this. So something that I want you to try in today's daily work. It'll be this question. This is an old AP question. All right. Some of you guys are really good. If you just kind of Google the first couple of words, you'll find the answers real quick. You're not being graded on this, but I want you to try this question on your own. You are certainly welcome to look up the answers afterwards, but I want you to think about this. This is a 10-point question. All right, so our prompt. A student prepares 100 mLs of a saturated solution of MgF2 by adding 0.50 grams of solid MgF2 to 100 mLs of distilled water at 25 degrees C and stirring until no more solid dissolves. Assume that the volume of the undissolved MgF2 is negligibly small. The saturated solution is analyzed and it is determined that the concentration of F- in the solution is 2.4 times 10 to the negative 3 molar. Write the chemical equation for the dissolving of MgF2 in water. That should be a very simple question. Calculate the number of moles of MgF2 that dissolved. All right. That should also be a fairly simple question. Determine the value of the solubility product, KSP, for MgF2 at 25 degrees Celsius. You are given the concentration of F- in the saturated solution. So think of it, that's kind of like when you get X in the other questions. I would make sure I have the reaction written out. Make that simple ICE table so you don't misuse this number, but you're going to calculate, you're going to solve for KSP. We've seen that in questions. That's nothing new. Part B, a beaker contains 500 milliliters of a solution in which both calcium 2 plus and barium 2 plus are present at a concentration of 0.10 molar. All right, so that means both of them are at 0.1 molar. A student intends to separate the ions by adding 0.20 molar NaF solution, 1 drop at a time, from a burette. At 25 degrees Celsius, the value of KSP for CaF2 is 3.5 times 10 to the negative 11th. The value of KSP for BAF2 is 1.8 times 10 to the negative 6th. Which salt will precipitate first, CaF2 or BAF2? Justify your answer. Well, what did we just talk about in this video? Look at those KSP values. This should be a really easy answer. Justify your answer. You want to explain it very succinctly. All right. I would perhaps mention something about Q and KSP. All right, to justify the answer. All right, because it's possible you may pick the right one, but not get credit for justifying. So I would mention Q. That's a pretty effective way. For parts BII and BII, assume that the addition of the NaF solution does not significantly affect the total volume of the liquid in the beaker. So calculate the minimum concentration of F- necessary to initiate precipitation of the salt selected in part BI. So again, the minimum concentration, that's right where the Q is just slightly going above KSP. You could basically think of Q equaling KSP here. And then for III, calculate the minimum volume of 0.2 molar NaF that must be added to the beaker to initiate precipitation of the salt selected in part BI. So if this is your concentration, now let's kind of think about it with the 0.2 molar. So that's all that question's adding. And now lastly, part C. There are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate formed in part B. All right. There was something really big we talked about on Thursday, a manner to get things to dissolve more. All right, so just think about both of them have that F minus anion. Is F minus, like what would it do in the presence of water? And what might make it better? So think about that for part C. Try this question today. All right, again, I will try to post a video today going through it. I know that there are answer keys online for this question. I just want to go through some of the more trickier parts, but try it on your own first. Look up one of those answer keys, totally fine. Email me a question if you're not sure about something that you've already worked through. All right, again, tomorrow I will definitely start chapter 17. I might possibly start it a little bit earlier today. We will see. So if I have the opportunity, I'll try to make more videos for you guys. All right. And this question, a couple of questions from the textbook will be your daily assignment for today. All right. So take care, guys. Be safe.